Okay, that seems to work now.
Yes. Okay, so we are live on YouTube. And okay, so hello, welcome to the third and final talk in Lisa Hartung's course. And just a quick note that we will have a final course next week by Miss Emiliano Gubinelli. The title and abstract will be posted online shortly and sent as well. So Lisa, please.
Okay, so yeah. Okay, so on Tuesday, I was focusing a lot on what somehow learning something about the path that a particle takes can help you, especially if you work with first and second moment methods. And I tried to convince you somehow that this can also be a multiple, that this process can have multiple steps, so that you can start with something rough and then get something finer and finer. And what I would like to focus on today is a little bit, how can we compare between the different type of models that I have been talking about? Because, so let me maybe just call this part comparison. Can you see what I'm writing?
I'm not seeing your writing. Yes, now it's okay.
Let's hope it works. Because so what is somehow the idea? Well, the idea is somehow in the case of the binary branching random walk, or maybe also in branching Brownian motion, we can do a direct analysis of the extremes. And also, on the other hand, in particular, when we work with Gaussian processes, let me just say, then we have more tools. So what I would like to talk about today is, on the one hand, what tools do we have to compare different Gaussian processes? Right, because maybe we have the two-dimensional discrete Gaussian free field, but we would like to compare it with something that we can directly analyze that lives on the tree, like the branching random walk. And on the other hand, I also would like to spend a little bit of time to say something about comparing with non-Gaussian, say, Gaussian models. With non-Gaussian ones. And I will start with the left-hand side. So I would like to start with telling you a little bit about Gaussian comparison. And the idea of Gaussian comparison is that you take the main idea is you take two independent Gaussian processes. You say that they have mean zero. And maybe they also have the same, and maybe they also would like to have the same variance. But that, you know, that we can keep for now as it is. Right? And now what Gaussian comparison tries to actually do is the following. You say, well, you want to say something like one is more correlated with the direction than the other. And then this has an implication on the maximum of one of them is larger than the other, for instance. Right? So you want to somehow interfere the knowledge. You want to say, if I know that the covariances are ordered, it also gives me an ordering of quantities I'm interested, observables of my process, right? And the easiest example that we have seen maybe, right? If we go to our binary branching random walk, well, we saw that the variant, and we compare it to 2 to the n IID Gaussians, right? Then in this model, both of these processes had the same variant, were mean zero, had the same variance, but the covariance is ordered, right? Because the covariance is this one here had as a covariance structure the overlap between the path, and here, if I take two different Gaussians, then the covariance is just zero, right? And we have seen in terms of the maximum of the one that has stronger positive correlations. Right? So we've seen that for the maximum, actually, the maximum of the more correlated object is smaller than the maximum of the IID object. And this can be put in a very general framework where you can say, well, I only need this order of the covariances to actually make this conclusion. And this is actually a very nice result due to Kahan that says exactly this. Right? Not exactly this, because the version I would like to give you, and now I have to kind of peek into how it's formulated, and I hope you can still see what I'm writing. So we take two Gaussian processes, X and Y, and we just say they are Gaussian processes. So let's just say they are n-dimensional Gaussian vectors. And we take two subsets, D1 and D2, of 1 to n cross 1 to n. So these are sets of index pairs. And we say on D1, the X process is more correlated than the Y process. Man sieht es. Yeah. Sorry, somehow this Zoom thing is. Yeah. Yeah, sorry. The problem is that I want to copy this from these notes to not mess up the signs. But if every time I look at these notes, it's not allowing me this. Let me try one thing. Because I attempt to mess up signs. So now it should be working. Now I can see everything. Okay, so we want to have on one of these D1, D2 sets, we want to have that X is, the covariance of X is greater or equal than the covariance of Y. So for all ij in D1, we want to have that the converse is true on D2. And we say, and then in principle, we could also, remove this greater or equal, less or equal, and just allow for equality in the remainder, I and j, not in this particular set D1 or D2. Right, so we have a specific ordering. And now if we take a function, if we take a function f, right, that's a function on Rn that has a moderate growth. And moderate growth in this case means that you can integrate it against the Gaussian density. And you say it's twice different, and you ask it to be twice differentiable. And you say that the second derivatives, they actually satisfy that they are greater or equal to 0 on D1. They are smaller than 0 on D2. Right, and you don't ask anything on the remaining indices because they're the covariances match exactly. And then Kahan's theorem says that if you look at the expectation of your function of one of the processes, x, then this is less or equal than the expectation of this function for the other process.
So are these processes assumed to be centered? So
Yes.
Zero?
Yes. So we center everything, and we want x and y to be independent. So I should also add this. And x and y should be independent. Right. So we think of X comes from one world and Y comes from another world. And we want to interfere something about the order of the expected value of some function of X and Y. And well, you know, if you look at extremes, right? So yeah, I add this as a remark. So one somehow very useful application, if you want to look at extremes, is that you look at Laplace transforms. Right? Because if you look at e to the lambda x and you take this lambda to be positive and you differentiate this function twice, it's a very nice function, right? Because you just get this, essentially you just get the lambda square e to the lambda x, and this has a nice sign. Right? So things that have exponential functions have the tendency to have good signs. Right? So and this is very useful, right? Because in particular, if you think about these class of Gaussian processes where we say, well, something is in this class if the covariances have roughly this or that form, right? Because the power of this, so the power of this theorem, which makes it so nice, is really that you only need, the only assumptions that you need to apply it are that the covariances are ordered. And often this covariance is the first thing that you kind of know about your Gaussian process. And the only thing that's maybe not very satisfying in this whole business is the fact that you need this function to be twice differentiable, right? Because for instance, well, no, so for instance, what you could say is, well, I mean, another function that maybe I would like to take, right, is this function, which just looks at the maximal value. No, but this is not a particularly nice differentiable function, right? So this is something you maybe would want. But in fact, the maximum can be nicely approximated by twice differentiable functions, right? So there's actually kind of a version of Kahan's theorem that looks at this maximum in particular, and this is what is known as Slipkinds lemma. In Slipkinds lemma, you take the same x and y as before, but now we are just going to assume that the expectation of xi, xj is strictly bigger than the expectation of yi, yj for all I unequal to j. And we assume that the variances match. And then Slipkinds lemma tells you that the expected value of the maximum of xi is bounded by the expected value of the maximum of the yi. Right? Right, so in particular, put this as another remark. If you can sandwich, so in particular, if you have if you have your model you're interested in, right, that has the covariance, whatever the covariance that you know, right, and you manage to sandwich it between another Gaussian process that you understand well, and the same thing on the other side. It might be two different processes. So it's Gaussian process, let's say 1 that you understand well, and Gaussian process that you understand well 2 on the other side. And you manage to say something about the expected value of the maximum here, and you manage to say something here, well, then you immediately get it for free for the model that you have in between those two. And there are more versions of this, right? So there's also and you can think of more functions that are not twice differentiable where you can actually use it, right? So for instance, you can also very explicitly so let me just put it roughly. Let me just say there are more functions connected to the extremes or the maximum where such a result holds. And in particular, what is really nice about what is kind of nice if you have Gaussian processes and you want to compare them is that the method of how you prove, so these seem to be very abstract theorems, right? But actually the method there, so the method, let's say a few words about the methods used to prove them, which are actually also, when you work with Gaussian processes, useful on their own, in the sense that when you cannot directly apply these theorems, you might actually want to go back to the proofs of them and try to tailor the proofs to the object you are looking at. So they are also useful on its own. And that's why I would like to spend, that's why I want to at least say a little bit about this. Because so there's a very nice, the very first very nice idea that is behind behind this Gaussian comparison is that you build, so the very first thing that you do is you build an interpolating Gaussian process XH whose covariance interpolates between the 1 of X and the 1 of Y. Namely, you choose this interpolation process as square root of H times the X process plus square root of 1 minus H, the Y process. Right, so if you put H equal to 1, this gives you exactly X. And if you put H equal to 0, this gives you exactly Y. And in between, it is something. Right? And this is made such that the covariance that you see of XH is exactly h times the covariance of x plus 1 minus h covariance of y. So this interpolation process that's used, it really linearly interpolates between the covariances of x and the covariances of y. And
So,
yes,
so for me, the very left side of the slide is cropped. I'm missing a couple of letters on the left.
on the left, you're missing a
Yes.
couple of letters. That's
Right.
weird.
This is true for others as well. Yeah, now
Yes,
fine.
I was wondering the same. Perfect.
Okay, not that I did anything, but I just moved the Zoom window to the right. Not that it was not on my screen before, but
Well, it was just 2 letters and now it's fine. So
okay, right. So, right. So the first very useful thing that you do is you build this interpolation process. And now there's another step that's really interesting, namely, what you do is if you look at the difference, okay. So now what you then do is somehow so now what you want to do is you want to you also give a name, so you define a function f of h that is actually the expectation of the functional you are looking at, but where you put the interpolating process. And now, well, what you are interested in is somehow gathering information on the sign of the expectation of when h is equal to 1 and the expectation when h is equal to 0. And now you can write this, very mysteriously as an integral over h ddh f of h. But now this derivative, this you can write explicitly. So this is, I will not do this here, but this you can write explicitly. So this is completely explicit. Okay. And right, so this is the first thing that you do, which seems a bit, useless as first sight, but it turns out to be very useful in combination with something else. The other good part that you learn, if you look at this proof in detail, the other good thing that you learn is that actually what is also a very nice thing is a Gaussian integration by parts formula. Which, it's really useful here, but it's also useful in other contexts. So here, for this, you take G of moderate growth, which means such that the proof goes through, which essentially means that you can integrate against the Gaussian. And you let it be from Rn R. And then you can look at the expected value of G of x times xi. And this you can write as the sum over all coordinates j is equal from 1 to n. And then you put the covariance of xi with xj, and then you put the expectation of the derivative with respect to the j coordinate behind this. And if you do this, right, in principle, so if you combine this step, so if you combine this explicit derivation of this f of h with a useful way, with using this Gaussian integration by parts formula, you can rewrite things in a way where you see the difference of the covariances appear. So somehow this here is the magic part where the covariance appears. If you build everything together, and this is somehow the part where you assume to know the sign. So this is somehow where the assumptions on the derivatives of the f's will come in if you would put everything together. But if you cannot, right, so if you cannot work with the Gaussian comparison theorems by themselves, it often helps to go back to the key ingredients. And the key ingredients are actually also useful by themselves. Right, and even the complete proof of these theorems is not too complicated. So these are somehow, so this refers to, let me write it, Comparinggaussian theorem. And if you want to work, if you were to work with functions that are not twice differentiable, you need to approximate them. And then take a limit, right? And usually need to do it a little bit careful, so you actually end up rewriting the, you sometimes kind of end up rewriting and going through these steps again. So maybe to be slightly less abstract, if you want application. Namely, you can look at what I will refer to as two-speed branching random walk, where the first n over 2 levels get an increment that is n0 sigma 1 squared distributed. And the others n over 2 levels get an n0. So you just put the different variants and you do it such that n over 2 sigma 1 squared plus n over 2 sigma 2 squared is equal to. Right, and if you draw a you could now draw a picture of these covariances or of the shape, the correlation function somehow. Right. So if I here put the possible overlaps of my path, so here I'm not, let's just say here's n and here's n, then somehow I can break this picture now. Now I can look at all these sigma 1 and sigma 2 values. I can break this picture at n over 2. And then I get exactly the model where this would correspond to slope sigma 1 squared and this gets slope sigma 2 squared. So this is a representation of the covariances. As a function of the overlap. Right? And now Gaussian comparison would tells me the following. Well, if I look at different functions, right, that are of this shape, then Gaussian comparison tells me that the expected value of the maxima are ordered. Namely, as I make my system more correlated, the maximum needs to go up. Needs to go down, right? So lower functions have higher max. In this language. Right? So really, as soon as you can draw pictures of your covariance functions and you can somehow intertwine them, draw them on top of each other, you have an ordering of the maxima. And you can also get, even more through these Laplace function, through these Laplace transform that you could also look at, so that also other quantities related to the characterizing the extremal process are actually ordered. Right? So this is actually useful. So this is somehow one toolbox I wanted to mention today. And I know I have been very abstract here, right? But I somehow believe that these are theorems that when working with Gaussian processes, people should just have in mind because they are very handy. And not too complicated and technical to use, actually. So maybe let me spend now a little bit of time on the other type of comparison, namely comparing with the Gaussian model. And of course, there are several options that you could take. So the first remark in this respect, maybe I should do, I should say that this localization business also works for non-Gaussian stuff. But this idea of comparing a Gaussian model to another Gaussian model via saying they have roughly the same covariance structure. So I just add a little bit to it so that the covariance is strictly above, and I subtract a little bit so that I have another model that still looks pretty much the same, where the covariance is below, and then I sandwich it. So the sandwiching idea doesn't work. Right. And of course, there are different things I could do. I mean, I could try to do things that are more model dependent. But what I actually wanted to mention here is a technique that has been kind of, successful, especially when looking at models that are related to the Riemann zeta function, when you would like to compare a model that's not really Gaussian to the branching random walk case. Because actually, I think it's also a very nice. It's also a very nice tool that actually I had not really come across in this formulation before looking at these papers. So this is something in formulation I'm stealing from a paper. That essentially is part of the works of Louis-Pierre Aragon, and you can find it there. But also there's only reference from other sources. So what's used in these contexts it's a very Assine type of bound. It's useful. So what does this theorem say? The theorem says the following. So if I take Wj, j greater or equal 1, sequence of independent and then random vectors on RD together with the Borel sigma algebra and some probability measure with mean expectation Wj. I should not make a full face. And covariances. So this is now is a matrix which we call conv wj, and we define the m-step mean, mu m to be, so this is just the sum, j goes from 1 to m expected value of wj, and we define the sum of the covariances in a similar way. And we also need, because this is actually going to be a quantitative estimate, we also need lambda m, which is the smallest eigenvalue of the covariance matrix. And Qm should be the law of the sum of the W's. And then this theorem says that there exists a constant C, which only depends on the dimension d, such that if you look at the maximal distance in supremum's norm over A in curly A, where this curly A now is just some collection of convex or well measurable subsets of RD, then this allows you to really bound the distance of observing this subset under Qm, so under the law of W1 plus and so on Wm, compared to the Gaussian measure eta, which has the correct mean and the correct covariance. So this now here is the Gaussian measure with mean mu m, covariance sigma m. And this you can bound now explicitly in terms of this constant. Then you have, your smallest eigenvalue to the -3/2. And now what you have to control is the sum. J goes from 1 to m, the expected value of, okay, and now this expression becomes slightly less handy. So you need to control Wj minus the expected value Wj to the power of 3. And so this looks like a very long theorem. So what is a little bit the idea why it's useful? Why it could be useful? Well, the idea why in principle this could be a useful tool is that if you have if your model, right, if you are able to write your model that you are interested in terms of a sum of independent increments, right? In some, so these increments are what you call W, okay? Right? And in particular here, right? Note that you don't need them to be, you just need them to be independent, right? So they don't need to be identically distributed. Right, so you, in particular, you can allow for some errors there. So if you can write, so if you can somehow decompose your model in terms of independent increments, right, then this allows you to compare with the corresponding Gaussian object. The corresponding Gaussian measure. Yeah. And it turns out that, for instance, right. So this is right, and for instance, you could think of this Gaussian measure, right? So this corresponding Gaussian measure, right? This could now be, in principle, be some kind of Gaussian or very close to a Gaussian branching random walk. Right. Of course, right, this is only very powerful if you have a very good estimate on, if you have very good, if you have very detailed estimates for this part somehow, right? So, so the reason so somehow what's a bit of the, so let's say what's a bit of the difficulty, or what could be a difficulty, the difficulty somehow is that you need weather good bounds for the right-hand side of the inequality. Right? So it's not something super weak. So this has been, so maybe let me say this. So this method has been successfully used in Hartung. This is, I think, also where I learned this. Hartung, Berlioz method, Berlioz and Harper, where they look at the maximum of in the model of the Riemann-Zeta function. So it's called maxima of a randomized Riemann-Zeta function. And I wanted to mention it here because I think somehow in practice it's always good to have a toolbox of comparison methods, right? Because very often, unfortunately, very often in these log-correlated fields, you think, well, these models look so much alike in terms of covariance structure, so they should be exactly the same. But unfortunately, it's often really hard to come up with a good toolbox to compare different models. And so the two parts of this toolbox that I've mentioned today are, on the one hand, this Gaussian comparison technique, which is really powerful if you work with Gaussian processes, but unfortunately immediately completely fails if you're non-Gaussian, right? I mean, of course, if you can use the second part of the toolbox now, and you compare it to a Gaussian model, then you can compare this Gaussian model further to a Gaussian model that you understand even better. So the second part of this toolbox is somehow saying, well, there are at least some methods, maybe not as many as we sometimes wish we could have, but there are some ways at least how you can compare a non-Gaussian measure to a Gaussian measure. And of course, this is not the very only theorem in this direction. I mean, especially if you look at branching random walks, you could also try to work with local CLTs and say that, locally everything looks essentially like in a Gaussian case. But since I only had 1 hour, I figured I would pick out these two examples that, give you somehow tools to hand to compare models. And this is somehow also where I would like to wrap up this little mini course, right? So since I call this course, some useful tools, right? So somehow the useful tools I wanted to tell you about, maybe as a take-home message, right? So the useful tools somehow in this context are really understanding localization. And of course, they go all hand in hand. To really use the power of first and second moments. Okay. And then, of course, today I focused a lot more on this comparison techniques. So comparing Gaussian models via Gaussian comparison. And the last thing I quickly mentioned is to go to the non-Gaussian. Non-Gaussian ones. And I should maybe close this mini course by saying that, especially in the later part, there still is a lot to be understood. So there are many things that we can do for the branching random walk that we cannot, that is for the Gaussian branching random walk, that we cannot do for other log correlated fields. Okay, I think I would stop here, and I'm happy to answer questions if there are some.
Okay, so thank you. We can all unmute to thank Lisa. And I will stop the recording in live streaming, but we have time for questions.